Before we delve into the meaning of real value characteristic impedance, let's explore another perspective on it. To begin, let's consider a straightforward circuit problem. We have two impedances, Z1 and Z2, connected in series. We can combine these two impedances into a single impedance, Z3, by adding them together, which is Z1 plus Z2. Suppose we have an L-shaped layered network, as shown on the right, composed of Z1 and Z2. How can we determine its input impedance Zin? One approach is to combine the last Z1 and Z2 to obtain Z3 and then connect Z3 and Z2 in parallel to yield Z4. And next, we can connect Z1 and Z4 in series to obtain Z5, which provides us with the input impedance Zin of the L-shaped ladder network. Okay, here comes a tricky question. If this ladder network were infinite in length, how could we determine its input impedance Zin? You might be thinking, is this a joke? An infinitely long network? How could I possibly know what its input impedance is? But don't worry, let's see if we can figure it out. Although this ladder network is infinitely long, there is always an input impedance when we look in from the left to right, which we will call it Z0. Our objective now is to determine the input impedance Z0 of this infinite network. When viewing the network from the AB interface, the input impedance is Z0. However, since the ladder network is infinite, the input impedance should also be Z0 when viewed from the CD interface. Thus, we will use Z0 to represent the impedance looking to the right from the CD interface. Well, since the input impedance of this infinite ladder network is Z0, we can say that the result of Z2 in parallel with Z0 and in series with Z1 will be equal to Z0. According to this equation, we can determine that Z0 equals Z1 over 2 plus the square root of Z1 squared over 4 plus Z1 times Z2. Okay, as we also know, for an infinite lossless line, its distributed model resembles a ladder network. The input impedance is referred to as Z0, where Z1 equals J omega and Z2 equals 1 over J omega C. As a result, we can establish a relationship between Z0, L, and C like this. Assuming that the inductance L is sufficiently small, we can disregard the J omega L over 2 term in the middle equation, leading us to obtain the next simplified expression. If L is exceptionally small, to the point where omega L squared over 4 in the square root can also be ignored, we find that Z0 will be equal to the square root of L over C. Remarkably, this outcome coincides with the characteristic impedance Z0 equals the square root of L over C determined by the ratio of voltage wave to the current wave. Now you might be wondering, what happens when the value of omega L squared over 4 is too significant to disregard? We will examine this issue in the following video.